I'll be open.
Because this mean.
We're moving to inferences with means this time. Now, what was the type of critical value we used all the way through with proportions? We used z, correct?
Right.
That was our critical value. That was our test statistic for proportions. But what did we discover about means yesterday?
They don't work with
So let me remind you this. So we got our statistic plus or minus the critical value times the standard error or standard deviation, right?
the standard error changes.
So notice, and hold on to what Tyler's saying, I need you to pay attention to this. The standard error what?
Changes.
The standard error changes. If we use the standard deviation of the sample means, what can we still use for our critical value? We can use, so if we have sigma, we can use z. So remember guys, if we have sigma, right? If we have sigma, we can still use z. But how realistic is it that we have sigma and we don't have mu? Not very likely, right? So we want to recognize that if I have my standard error, sometimes that standard error is longer, sometimes it's shorter, and so we can no longer use z, we have to use what critical value? T, right? So for the vast majority of means, we're going to use the t critical value. And I'm going to show you a couple of things with that, but I just wanted that recap before we get going with today. What are your questions about that recap? Okay, so remember, your standard error, it can change with your samples, because is one sample always going to be the same as another sample? No, right? So that sampling variability exists, and we have to account for that. All right, so that got us through this set of notes. So this also answers this question: when should we use a t critical value rather than a z critical value for calculating a confidence interval for a population mean?
When we don't have sigma.
So when we do not have sigma. So when we have to, and I'll point this out, what is this doing in respect to sigma? There's a relationship between them, huh? It's estimating, right? This standard error estimates sigma. And so that's the language I'm going to include here. This should be your new notes from yesterday, Peyton. Do you know where you put those? You just look like you're trying to find these notes.
I just opened my thing up on it.
Okay. So when we have S sub x estimating sigma sub x, right? So when we don't have the standard deviation, right? So don't forget that S for the sample means is the standard error estimating the standard deviation of the sample means, right? That S for the standard error is estimating the standard deviation of the sample means.
How come standard error doesn't change proportions?
Because one thing you'll find out, okay, so let me explain it this way. When n is huge, I'm just going to use that kind of casually. When n is huge, that t value is actually going to approach z. And so when you think about your proportions, do we have small samples or large samples? I mean, it's usually hundreds, if not thousands, right? Or at least like 50 was like the smallest. When you get to a large enough sample size, that t value is going to approach z, and so we just use z. And so you'll see some textbooks and some resources talk about that confidence interval, that hypothesis test, as a large proportions or something like that. So we don't have to worry about t when we have z like that. Does that make sense?
Yeah.
Okay. Or we don't have to worry about t when we have large sample size. When we work with means, we're going to be dealing with sample sizes of like 4 and 8 and things like that at times. And so we have to use t, especially in that case. Okay? Okay, so let's look at some information from the book. And so I want you to see something about the t critical value from the book information, right? Nope, not that one. So chapter 10. Did it say page 652 to 650 something?
655.
What's 62 to 65?
Say that one more time.
652 to 655.
55, okay, cool. Alright, so, I'm going to make it nice and large up on the board. So, it talks about calculating a T critical value here, 652 literally. And so, remember that confidence interval has not changed. And so it is no longer a one prop Z interval. What are we going to call this one?
One mean
It's right here. One
sample.
sample T interval. When you see one sample, one or two sample, we're talking about means in that case, not proportions, right? So one sample T interval for a population mean, because what are we estimating? Population mean, right? One thing I'll say, I just want to remind you, and we need to be careful, because a couple of you missed easy ones on that multiple choice that I know you know, but we have to pay attention to details, because we picked answers that were about the samples and not about the population. You've got to be attentive to that detail. All right, so right here, okay? So the T critical value changes according to what we call degrees of freedom. All right, I'm going to come back to that word in just a second. I want you to see these different, so these are our T distributions. If you look here, this distribution, that's my Z distribution. Right through here, there's Z. Now, those other ones are not very different, but what do we notice, or hopefully what do we notice about those distributions in respect to the standard normal?
They're lower and freedom.
So there's those degrees of freedom, but you talk about they're lower. So if they're lower, what are they also going to be?
Less varied.
More varied.
They're going to be more varied. Look how they are wider. If they're shorter, because remember, how much area is under that curve, no matter what?
No.
The area is always 1, right? So if it's going to be shorter, it's also got to be wider. Notice, and I'm just making this up, if this is 95%, right, for my standard normal curve, well, I've got to get out to here to get the same area because it was shorter and wider, right? And so when I talk about those T critical values, the lower the degree of freedom, what's going to happen to that curve?
It's going to expand.
It's going to expand. It's going to be wider out, right? So we're going to get larger critical values to account for this. And so degrees of freedom. Remember how we had S sub x was estimating sigma sub x, yeah? Okay. So how many things are we estimating from the population when we do that? We're trying to estimate the population mean, but we also are having to use S sub x bar to estimate sigma at the same time. So we have one extra estimator. So the degrees of freedom is n minus 1. Where n is the what? Not the number of estimators. N has not changed since we started studying the statistics. N is just my sample size, right? So whatever my sample size is minus 1, that's what the degrees of freedom is. When my degrees of freedom gets really large, we're basically going to approach the standard normal curve. So if my degrees of freedom is 2, what's the sample size there? 3. The degrees of freedom is 9, what's my sample size there? Okay. It is actually very heavily related to chi-squared, which is what the unit after this one's going to be about. I might push that for 2 units, but I could do a couple of things. All right. So, there's something I was going to say with this. Okay, so let's say, because I want us to understand how to calculate a critical value, let's say I want to have 98% confidence with a sample size of 8. Okay? So, what do you already know based on last unit that could help us find the critical value, which am I going to use Z here for my critical value? What am I going to use?
T star.
T star, right? I'm going to use a T critical value now. So I want 98% confidence. I want a sample size of, with a sample size of 8. So how am I going to calculate? What do you know that can help us find that critical value?
Formula.
What formula?
Standard error. No.
I just want the critical value. It's not standard error.
Where's the critical?
So inverse what? So let's think about it. Is this a normal curve?
Yes. Yeah.
It's close. But remember, the normal curve is z-scores, huh?
Oh yeah.
There's a what option?
Inverse T.
There's an inverse t. So first things first though, I'm going to highly recommend that you draw a curve, right? To help you visualize this, I want what percent of data do I want in between my critical values? 0.98. So what would be to the left of here?
0.01.
0.01, right? 0.01 here, 0.01 here. And so I want you to do that inverse t, see what critical value you get.
What's the degree of freedom?
It's a great question. You know the information. Think about what information I gave you to figure out that degrees of freedom.
No. You said.
Ah.
What's the sample size?
Say again.
What's the sample size for this then?
Look at what I wrote up on the board. I already told you.
It doesn't.
It's under distribution.
Well, I looked under it.
See the inverse t there? There you go.
Wait, so how are there decimal points of freedom though? Like how's it saying 1.2 degrees?
No. You did TCDF.
5 hours.
Remember, that takes a value and gives you the area. You have an area.
If the
No,
sample size
close.
minus
Sample size
One. Guess what I'm putting?
1 minus 1. You added.
Hey,
I gave you the sample size.
if the degrees of freedom in minus 1,
Yeah.
how is it 1.2? No, wait, that's okay, I thought it said 1.2.
What do you mean?
So notice right here, so what you did the 0.98, which is only this. When you do that inverse t, you always need a tail, right? So you could have used 0.01 or you could have done 0.99. You had to do 0. Hey, so really quickly, right? I wanted to remind you, okay? If you put the area of 0.01 in here, what t critical value did you get?
About -3.
-3? For real, exactly?
It's not negative 2.9.
Okay.
Okay.
That was luck. I did not intend that. -2 point what?
What if you rounded it?
Yeah, we're gonna go with -3. That's close enough for that rounding. Okay, so just based on that, that's wild. That was luck. All right. So what would this critical value be if you put the 0.99 in? 3, right? So remember those two tails should give us the exact same critical values, right? So you could have done the 0.99 because it's always whatever's to the left.
Oh, wait. So we don't do 9.98.
No, because remember, when you do inverse normal, when you do the inverse t, it always takes the area to the left, right? So you need all of the area to the left. So you could have either used the 0.01 or the 0.99, which would include the 0.98 and the 0.01. All right.
Have you gotten the fair models for this unit yet?
No, I'll get those to you on Monday. Alright, so one thing to be aware of, it even says it here in the book. We're going to learn more about the t distributions themselves in chapter 11. We're just focusing on how to calculate the critical value, right? So we're just focusing on how to calculate that critical value. Now, the textbook does go into how to use the t chart, which is a part of the formulas. But guys, I'm not even going to waste your time teaching you how to use the charts with normal distributions and t charts because we've got calculators, okay? I might show it to you if we have time to review just quickly, but we ain't got that time right now. So, write down your notes about how do we calculate the value of t star, how do we calculate degrees of freedom. If I need to rewrite anything or clarify anything, let me know.
So what was the part about it being huge?
Did we talk about calculating this?
What did we just do?
Oh, no, wait, I thought it was saying just T.
Right, so how do we calculate T star? By using that inverse T, right?
Yeah.
So guys, write out whatever notes you need to about how to calculate that T star, how to calculate that degrees of freedom.
It's like spring break, I was trying to think of I just changed to like a plus or a shot.
Okay. Yeah. When you can make it work, you can make it work,
Well, you're
right?
the smartest person in class.
Or you do the divine.
But I ran the table out.
I don't think so.
Because you can
Yeah.
use this and go to the
So Peyton, do you have all the notes you need to about how to calculate T critical value?
We're working on it.
What's the thing?
Nobody knows. Nobody knows what's going on.
You have such a fatalistic attitude, it's beautiful.
No, I'm
It was like a V.
What?
Fatalistic attitude.
That nothing matters, nothing,
Oh.
No,
whatever.
not that.
That
Good lord.
everything is bleak and awful.
Except for sleeping. Sleeping ain't like awful. I love sleeping.
I'm fatalistic towards calculation.
Alright, here's 2 quick practice problems. Try A and B underneath those notes. If you need to finish your notes, do it. But after that, do A and B.
Sorry.
Right. Guys, I need to have these T critical values calculated within the next 90 seconds.
Oh, wait.
Guys, it's using a calculator.
I was about to say, we didn't know how to do this.
What's the area?
It's weird because I'm,
Oh.
no, I'm not using this. So we're gonna do distribution, we're gonna do average speed, and 90% confidence factor. What would our area be? 90? What our confidence equivalent? Is 0.9. And then our degree of freedom would be what?
Yeah, with Ashley got.
What our degree of freedom would be 0.9.
So A, I got 1.833.
Where did y'all get it?
I got negative 1.8.
Oh yeah, we're just
I got 1.83, yeah.
0.05.
I think I did.
Yeah, 0.5.
Because you have to do the two sides.
I got it.
Oh, what?
The two sides.
Our degree of freedom is
So
what?
you put like plus or minus?
Because it's n minus 1.
Or like, cause it's
Yeah.
both of them? Or no? Or does it
Yeah.
matter?
Guys, I actually know
But
how
Tyler
to do
got
something
negative
for once.
five.
I'm so happy.
I just did that.
It's a negative one, right?
You get it?
Crazy, whenever you're awake, you can do stuff.
I'm never awake. I'm so
No, it's just
selective.
area.
I was like, this man is always sleeping, he just doesn't know it.
I'm dreaming. What would that be? 0.005? And that would be 2.6.
Now I got it.
Good stuff, good stuff. Did you already got 1.0?
And 1 for
I feel like that.
Okay,
We did great.
those are the T critical values that I calculated. Do I need to
Can you circle it?
1.83 for A, 2.64 for B.
Can you just get rid of the negative numbers?
Never mind.
Nothing hard.
Never mind.
Just rounding. What? Notice I identified my degrees of freedom. 2.64. By the way, I do want to point this out really quickly. Does anyone remember what the Z-score was for a 99% confidence interval?
No, like one.
It was
Not for 99%.
0.99.
2.576.
Wait,
Notice, I just want you to notice,
I got
you see how that's only a little bit more than 2.576?
I mean, that's a good bit.
Why did you tug on it?
Not as much, so like, think about this. So pay attention to this, guys. Hey. For the 90% confidence interval, Z was 1.64. That's a full 0.19 more.
I mean, it's enough where we're not using Z, so.
I know. But my point is this.
Oh, yeah.
Notice how that's only 0.06 something? My point is this, and I want you to understand. As my sample size increases, my T distribution gets closer to the Z distribution. Okay? So please notice, that's all I want us to see out of this, that for a degrees of freedom of 9, a sample size of 10, the Z and T are pretty far apart. But as my degrees of freedom increases, the z and t become much closer, right? Because there's less variability, there's less spread when my sample size increases. That's all I wanted us to understand. So notice, like, yes, they're apart, but not nearly as much. It's like a third of what this was.
Yeah.
Okay? Questions about calculating t star? Haley, you with me?
Yes.
Okay.
Sorry, I'm trying to look at everything.
What just happened? Alright. So, meant to get there yesterday. So here's what I gotta ask. Here's something that you already know. Let's think about this logically. 3 conditions for constructing a confidence interval for population means.
Random. Large counts.
Large counts, you think?
No,
Hopefully.
10%.
So we need random. We always need random, otherwise our data sucks. 10%, right? That each individual value is independent of each other, so the 10% condition. But you said large counts here.
I was kidding.
You're kidding? What do you think it's going to be instead?
Oh, wait.
Small counts.
It's not small count, say it again.
Central limit theorem.
So remember, guys, large counts condition helped us check that a sampling distribution of proportions was approximately what? Normal, right? But for means, we need the central limit theorem. But pause for a second. I need you to pay attention to this. I just told you we're going to be doing stuff with means with small sample sizes, right? So we always going to have a sample size greater than 30. So what's another condition, or what's another way to know the sampling distribution is approximately normal?
If the original is already normal.
So if population distribution, so central limit theorem, or if population distribution approximately normal. But if we knew the population distribution, yeah, how likely is it that we don't know the population mean and the population standard deviation? I would say if we already know what the population distribution looks like, so there's a final and third way, okay? And this is something you want to pay attention to. Or if the distribution of the sample is approximately, or roughly, I should say roughly here, roughly symmetric, what we will say is it's believable. Sampling distribution is approximately normal. Hopefully we satisfy the central limit theorem.
What do we need normal sampling distribution for if we're using T-star?
Yes.
Actually,
Well, it would have been normal, but it would be symmetric. So I will point this out. That standard, so like the t distribution is not perfectly symmetrical because 95% of the data, or 68% of the data is not within one standard deviation. 95% is not within 2. So it is still bell-shaped, it is still symmetrical, but it's not normal. It is symmetrical though, which is why if the distribution of the sample is roughly symmetric, we will say that it's believable the sampling distribution is approximately normal.
all I'm saying, like like if we're using T-star, do we even need a normal sampling distribution?
Yes. I see what you're saying, but it still needs to be that bell shape. It still needs to be symmetrical. But that's why we say symmetric here instead of saying it has to be the sampling, or this has to be approximately normal. And again, that's why we say it's approximately normal. It's not actually normal, but it has a lot of those characteristics. Okay? So notice how much of those conditions changed.
Just one.
Just one, but even that one, is it completely different?
Yeah.
Is it?
Well, never mind.
What was the point of large counts? That my sampling distribution was approximately normal. What is the point of this whole section? That the sampling distribution is approximately normal. So it's just that with means, we have a different way to check normality, right? So make sure you have those conditions, and again, remember, we still always need a sampling distribution that is approximately normal. So why do we check these conditions? What happens if they are violated?
We kind of like can't really do it.
So it's not necessarily bad data. The bad data just comes from random, right? Our confidence interval is completely out the window if the data is not random, if our data is biased. But what happens if we violate the 10% condition?
It's not.
What happens if it's not approximately normal?
It's not independent, and then if it's not normal.
Okay,
It's
The samples affect each other.
okay, yes. But let's say I want a 95% confidence level. What does that mean?
No, it's not confident.
I have 95.
So in the long run, how many of my intervals should capture the parameter? 95%. However, when we didn't use T, right? When we didn't use T, we didn't have the right capture rate. If it's not approximately normal, we're not going to have the right capture rate. If we violate the 10% condition, it's not going to have the right capture rate. If you violate 10%, it actually has too high a capture rate. And so you might be like, oh, that's fine, but no, it's not, because then we don't know what the capture rate is. If we violate the approximate normality, it has too low a capture rate. And so what happens is we have the wrong capture rate. We want 95% confidence level. We want 99% confidence level. If we violate those conditions, and so yeah, if we violate random, the data sucks. We definitely have the wrong stuff there. All right, I know.
We have 10 seconds.
I know. We are going to pick up there on Monday, and we're gonna have to try to move quickly because, guys, I don't know if you looked at it, but we got 4 weeks.
That's not
Let's go.
We got 4 weeks, and I got to finish this unit and do one more full unit and one mini unit. My goal is that we'll finish this next Friday, test on Monday.
At least chi-squared might not work.
No, chi-squared is not. Chi-squared is very, very good. The one thing about chi-squared is it'll be a little bit different in stats than it was in bio.
Bio